As example, let's see modeling of emission properties of the argon gallium iodide 3 positive column discharge plasma using the Chemical Workbench computational environment. Modeling of argon gallium iodide 3 positive column discharge plasma will be carried out using non-equilibrium plasma chemistry reactor with electron-stimulated and vibration relaxation reactions, in which the time evolution of chemical composition and gas parameters appears under the effect of chemical reactions, gas-plasma interaction, and radiation at constant pressure and temperature. In this model, current through a discharge is set by hand and is Fermi-like function of time, and electric field intensity is determined in self-consistent manner by current density in plasma. The reactor model is based on numerical solution of the Boltzmann kinetic equation for electron energy distribution function in low temperature plasma and determination of rate coefficients of electron-induced chemical reactions, energy distribution, and electron swarm parameters in gas discharge. Gas composition in the reactor is changed as a result of chemical and electronic kinetic plasma. The calculation yields the electron energy balance, emission spectrum, and the emission efficiency as function of plasma parameters. The final goal was to predict the emission spectrum and power in the ultraviolet and visible range, and the emission efficiency. Now we will start plasma project in Chemical Workbench. Let's open the project, which allows us to modeling positive column discharge plasma. Click File in main toolbar, Open. The window Open Project will appear. We choose Vibrokin examples gallium iodide 3 discharge project file. Wait when project is completely loaded. Project contains table of substances and reactions, input stream and calculation, field and model parameters. All species used in mechanism can be seen by double-click on Substances tab. You can see neutral, excited, and charged species of gallium iodide and argon, electrons, and gamma quantum emitted during discharge. Full table of plasma chemical diffusion reactions and reactions of light emission can be seen by double-click on Reaction tab. A set of electronical and chemical processes are included in the kinetic model. Chemical processes of neutral species, ion molecular reactions, elastic electron atom and electron molecular collisions, electron impact dissociation of molecular, electron impact excitation of atoms and excitation of moleculars, ionization from the ground state, stepwise ionization and pinning processes, emission processes, recombination of charged particles, attachment and detachment processes, diffusion of atoms to the tube wall, ambipolar diffusion processes of ions and electrons. The plasma code includes a database of well-established set of cross-sections of electron-neutral collisions, which can be extended by user-defined cross-section in common table format or using one of analytical representations of electron-neutral collisions. Input stream parameters can be seen by double-click on Input Stream tab and contains gas mixture composition, temperature, pressure, and others. We can input flow rate in desired units, temperature in kelvins, and units of gas mixture composition. Our mixture is composed of neutral species, argon and gallium iodide 3 molecular, and charged species, electrons and positive ions of argons with identical amount to make the plasma electron neutral. The gallium iodide 3 concentration is set equal to corresponding saturation vapor pressure for given cold spot temperature. Initial concentration of ions and electrons are the priming concentrations for establishment of steady state during low discharge. project contains some calculation parameters which are necessary to provide a successful calculation process. Some of that are many important. Two types of calculation of electron energy distribution function are supported. Dynamic means that EADF and the rate constants of electron-stimulated reactions are calculated during kinetic modeling for the given gas composition and electric field intensity. Approx mode means that EADF and the rate constants are calculated as a function of reduced field intensity before kinetic modeling and are approximated by analytical dependencies. In our calculation parameters, EADF mode must be equal to dynamic. Electron-electron collisions and superelastic collisions must be turned on. EADF will be calculated within values of maximal and minimum electric field. Field model parameters are also very important and contains parameters of electrical circuit. The reduced electrical field strength is established automatically during the calculation run in order to obey the electron number density balance to maintain given current. Initial field value for zero time point is equal to 100,000. Current through a discharge is set by hand and equal to 1 ampere. Length of discharge is equal to 1 cm and cross-section of the discharge channel is equal to 5 square centimeter. The model parameters contain input pressure. Calculation time will be enough to reach the steady-state species concentrations during low discharge, temperature, channel radius. Plasma reactor has various diffusion models which can be used in calculations. Diffusion of vast neutral and charged species can be turned off. Wilkie diffusion model is diffusion of only neutral species. Ambipolar diffusions of electron positive ions and tripolar diffusion of electrons positive and negative ions. In our calculations, diffusion model is equal to ambipolar. Now we complete the parameters of our simulations and we can start it. Please click Run button at the main toolbar. Program makes verification of the mechanism and starts calculation. All the results in data table of results tab are automatically updated. When simulation is completed, all available results of our glow discharge simulation will be shown in the data table of results tab. Following results table are available for full time scale and for all input parameters of calculation. Distribution of energy by channels, distribution of energy by processes, EADF function, G factor. General results tables contains species concentrations, full reaction rates, gas mixture and discharge parameters such as temperature, density, thermodynamic function of mixture, which can be plotted on graphic figures. Rate coefficient tables, swarm data, and tables of electric circuit parameters. For example, we can see time evolution of species concentrations during low discharge. Figure shows concentrations of gallium atoms in ground and electronic excited states, electrons and positive ions of gallium versus time. At time 0.001 second, concentrations reached their steady state values. Another figure demonstrates the distribution of input energy over various loss channels for time point when steady state conditions were reached. Main loss channels for present low discharge conditions are elastic scattering of electrons by argon atoms, excitation of gallium atoms to metastable state, and excitation of lower radiative states of atomic gallium. The final goal of our model is to predict the emission spectrum and power in the ultraviolet and visible range, and the emission efficiency as function of plasma and input gas parameters for various gas composition. Left figure presents gallium iodide spectrum calculated in argon gallium iodide 3 gas mixture under glow discharge conditions. Argon gallium iodide 3 spectrum taken from experimental results is shown in the right figure for comparison. The calculated spectrum is in a qualitative agreement with experimentally measured, so plasma reactors allow to calculate various discharge type in various gas mixture for wide range of input plasma parameters.